Hey everyone. So today we'll explore the IMDb movie database and the WHO's life expectancy database and perform some hypothesis testing, exploratory data analysis, linear regression, logistic regression, try using the KNN algorithm of classification, the random forest classifier, and then we'll look at the results and plot the same. So with that as the objectives for the video, we'll go through them by going through the code. We're using the Python programming language to do the analysis and Google's Colab notebook environment to do the same. So the first cell is basically all of our imports that we'll be needing for the analysis that we are going to be performing. So we are using the statistics library, the NumPy library, pandas, matplotlib, scikit-learn, scipy, and cbon. Now that we've linked the Colab environment with our Google Drive storage, we can start the analysis. So first, let's go through the IMDb database, which provides a bunch of TSV files which have the following. So as we can see, title basic is basically a TSV file with the following fields: title type, primary title, original title, and a bunch of other attributes that are not necessary for our analysis. And titles AKAs have the following attributes. The IMDb database is a huge database which has more than 10 million movies indexed within it. So the first section of our video is going to be the hypothesis testing. So let's define our hypothesis. So our initial hypothesis, or the null hypothesis denoted by H0, is that the region and the runtime of the movie are not related. So this is our initial null hypothesis. So what this means is that the region in which the movie was released is not correlated to the runtime of the movie, which is defined in titles basic. So we have to merge these two databases, data frames, and that's what is done here. So our alternate hypothesis, or H1, will then be that the region and the runtime are related. So let's go ahead with performing the hypothesis testing. So this part of code merges these two data frames and then basically provides us with the data frame that we need with our analysis as shown here. So now we have a data frame that lists the region of where a movie was released and its runtime. Now the IMDb database has more than 10 million movies and has regions which have less than 5,000 movies, and they can act as noise in our database. So the initial steps that we are doing onto the data frame is basically pre-processing that included removing values which didn't exist and filtering out regions which have less than 5,000 movies, and that is exactly what this code does. And as we can see here, the final dictionary here shows the regions which have more than 5,000 movies and are actually relevant for our hypothesis testing. Now we have selected India, Japan, Mexico, Denmark, and Great Britain for our analysis. Now we have selected these regions considering the cultural differences among them. Now we are going to extract only movies which were released in these five regions. Now the reason why we selected 5 regions is since when you're performing hypothesis testing, it is better to have a lower number of variables because the degree of freedom while performing the chi-square test can explode and give you insignificant results. Now the runtime minutes here is a continuous variable, and since it is better if we have categorical variables, we are going to bin them into these groups. If the movie is between 0 and 60 minutes, if it is between 60 and 120 minutes, and if it is between 120 and 180 minutes, and if it is more than that. Now, after performing this, we have a final data frame that looks something like this. Now we're going to calculate what's called a crosstab. Now, what a crosstab basically is it's basically a frequency table of a variable when compared with another. And this is a crosstab that is the result of this operation. Now, what this signifies is that there were 1,152 movies that were released in Denmark with a runtime of 0 to 60 minutes. Now, the way hypothesis testing is done is by calculating what's called a p-value and comparing it with alpha, also known as significance factor. Now, the significance factor denotes the probability of ignoring H0 even when it is true. And what 0.05 signifies is a 5% chance of ignoring the null hypothesis even when it is true. Now, after performing this operation, we see that the p-value is 0 and it is lesser than our significance factor, and hence our hypothesis is rejected, meaning that the runtime and the region were in fact dependent. Now, the result of the hypothesis testing basically gives us a go-ahead for performing other types of analysis and evaluations on those two selected attributes, which were runtime and region. Now, let's go ahead and do some exploratory data analysis on the IMDb database and try to find if there is any pattern that is observed between the start year of the movie and the number of movies that were released. The following code generates a dictionary with the counts of the number of movies released in a particular year and also plots the graph and the relation between the same. And as we can see, in the 1880s, when technology really wasn't that widely available and the movie industry wasn't that big, the number of movies that were released is very low. And come the 2000s, the number of movies released and indexed shot up. And since it is 2020, a lot of movies haven't been indexed yet. So this graph shows the exponential distribution of the number of releases per year. In the next part of our video, we'll try to find out if there's any relation between the runtime minutes of a movie and the number of movies released with that runtime. We are going to need to create a histogram for this, so let's go ahead with this. So we're using the title's basic data frame since it has the runtime minutes for a movie. Now we are only interested in movies in the range of 30 minutes to 3.5 hours, since there are exceptions of 20 hours that can skew our graph. So this is a probability distribution of the runtime of movies, and as we can see, 90 minutes turns out to be the most common runtime, with over 35% of movies falling within that runtime. And the following is the cumulative distribution of runtime of movies. Now, when the mean, median, and mode is calculated for our data, we observe that the mean, median, and mode are all roughly 90 minutes. And that is because the pattern and the distribution of the runtime as observed here is similar to one of a normal distribution curve where the mean, median, and mode are of the same value. Now that we have performed hypothesis testing and have done basic exploratory data analysis on our data sets, we can go ahead in building models. The first model in this video is going to be the linear regression model. We're going to be performing linear regression on the WHO's life expectancy database, which is a CSV file which has attributes of adult mortality, infant deaths, alcohol usage, BMI, etc. to give a value for life expectancy, as we can see here. Now, the first step in finding out which attributes to pick for linear regression among the many in this database is by measuring the correlation and covariance among the attributes. So let's do that. We pick attributes that have a high value of correlation with life expectancy, such as adult mortality, which has a negative correlation of 0.7, and alcohol usage, which has a positive correlation of 0.4. What this means is that these attributes have a higher impact in predicting life expectancy than, say, the year, which has only a correlation of 0.1. The following attributes are chosen to be part of the linear regression model. We're using the scikit-learn's linear regression model to perform the linear regression, and we have chosen a test size of 0.2%. We fit the model based on x, which is our attributes, and y, which is our target values. And then when we see the scores of our linear regression model, we see that our model has an accuracy of about 82%. And these are the other error metrics that are used while evaluating the performance of a linear regression model. Now let's move on to classification algorithms, starting with logistic regression, which is going to be performed on the IMDb dataset. Now let's try classifying if a movie is a short movie or a full-length movie based on its runtime. This part of code does the data pre-processing to remove erroneous entries within the dataset. Now we assign a numeric value to the labels to which we are trying to classify. So if a movie is a short movie, it gets assigned the label of 0, and if it is otherwise a full-length movie, it gets assigned the label of 1. And we are again using the scikit-learn's logistic regression model to perform our logistic regression. So let's see what the accuracy of our model is. And we see that our logistic regression classifier has an accuracy of about 98% in predicting if a movie is a short movie or a full-length movie depending on its runtime. And this is the classification report for our logistic regression model. Now let's go ahead with the KNN algorithm of classification. We'll perform the classification on the same problem statement of classifying if a title type is a full-length movie or a short movie based on its runtime. In the data pre-processing step, we prepare the data for the classification and assign a label for our target value, and if it is 0, it is a short-length movie, and if it is 1, it is a full-length movie. And we're using the KNN classifier class provided by the scikit-learn library to perform our KNN classification. And we're setting the n neighbors to 800, which is dependent on the size of the input. And this is the accuracy of our model, and this is the classification report of the KNN classifier. Now let's see the random forest classification algorithm for the same problem statement as of the k-nearest neighbors algorithm and the logistic regression. The same pre-processing techniques are applied as the KNN algorithm and the logistic regression by attaching the label for our target value. We're using the scikit-learn's random forest classifier class for our classification. And we see that the accuracy achieved by the random forest classifier is 99%. And this is a classification report for this algorithm.